In contrast, precious metals distinguish themselves because they are resistant to oxidation. So chemical inertness makes them be identified as noble metal. Cookson and others have typically used 3D printing of precious metals to not only make these jewelry items such as these cufflinks, but also for dental applications. In addition to just being expensive and considered for jewelry, they have typically high density, they have good ductility, high electrical conductivity, high corrosion resistance, and have catalytic properties as well. Palladium is a good example of such attributes. Refractory metals. Uh, Tungsten is an example over here of a material that is shown. Here are X-ray collimators made at UFL. So a few designs by some design teams. Molybdenum, niobium, tantalum are all examples of refractory metals. They can endure high temperatures. They have high density, niobium being the exception where its density is less than that of steel. Yeah, they have high hardness at elevated temperatures. Copper alloys can be easily processed into a number of shapes by traditional methods, including casting. They're ductile, they're malleable, they can be formed into different shapes. Characteristic properties for use include electrical and thermal conductivity. If you add tin to copper, you make a bronze. If you add zinc, you make a brass. You can make corrosion resistant fittings with bronze. It has that characteristic because tin is another the oxide on tin is noble. You can make very attractive components using these as well. A lot of hardware, a lot of marine corrosion resistance characteristics with the brasses and bronze. Nickel alloys, besides the super alloys, include Monal, and that also has great corrosion resistance, has good heat resistance. Typical uses of nickel include plating for electronics, use of thermocouples, different kinds of brasses. Magnesium alloys stand out because they are lightweight and they can be processed at low enough temperatures. Magnesium powders are also used for fireworks, as are many other metal powders. So got to be careful when making things out of these. But it appears as though there are some nice opportunities for using magnesium alloys for aerospace industry, for automotive industry, to make lightweight structural parts. Here's an engine block that's shown, produced by at the US Department of Energy. So in summary, majority of additive manufacturing is dominated by powders. Variation of powder attributes can affect processing conditions and also the resulting properties. Sintering gives avenue for making components out of powders traditionally. It's also utilized in a number of 3D printing avenues, but you can also increase the energy to the point that you can melt those regions completely for densification. A few stainless and tool steels and a lot of non-ferrous alloys dominated additive manufacturing, in contrast to ferrous alloys dominating traditional manufacturing routes. In the next class, we will talk about a few metal processing methods, and here's an example of a component made by GE Aviation.